In this video, we're going to talk about digital communication, the transmission of bits from one place to another. Turns out that most channels for even digital communication applications are analog. So we have to worry about how we send those bits. What is a good choice for the signals, the analog signals to use, and what are some bad choices? Well, since the channel is also analog, we have to worry about how much bandwidth is being used to send that bit sequence. It's going to become a very important consideration. So let's get started and develop what's called the digital communication model. So here I show a situation similar to what we've already talked about in terms of analog communication, in that I have an analog signal, a message M, that's to be sent to the sink. Now, what we're going to do, as opposed to the analog situation where we automatically send that to the transmitter to modulate it, let's say, here we go through an A to D converter to create bits. Those bits have to somehow be related to an analog signal that can go through our analog channel, be it wireline or wireless. The receiver then will convert that analog signal back into a bit sequence, which then goes into our familiar thing, the D to A converter, and to produce the message that was trying to be transmitted. So it's a complicated sequence of events here, much more so than the analog case, but there are some real advantages and some disadvantages, and we're going to talk about those as we go through. There are also situations in which the message is inherently digital, a sequence of bits. And what I'm thinking about here is text. Text is automatically a sequence of bits. There is no A to D converter at all. So the same model and processing that I have in both of these are the same. It doesn't really matter, except there's no A to D or D to A in the digital message case. Still have the problem of how do you assign analog signals to bits, and how do you undo that to receive that bit sequence again. The channels are all analog in almost every case. So it turns out assigning bits to analog signals is a pretty easy task. What we're basically going to do is assign a signal, a specific signal for each bit. We're going to have a signal that represents a 0, a different signal that represents a 1. Those two signals, whatever we choose, form what we call a signal set. Let me give you a simple example. And this is the simplest digital communication case that we have. It's called BPSK. It stands for Binary Phase Shift Keying. Keying is an old word which comes from the telegraph days, which sending dots and dashes is the same as sending zeros and ones in many ways. So that's where the terminology is borrowed from. In binary phase shift keying, whatever signal you use to represent one bit, here I have a positive pulse to represent a 0, the other signal is the negative. And that defines a binary shift keying signal set. In all cases, one signal is the negative of the other. Now in the case I've shown here, you could consider this a baseband signal set. It exists at low frequencies. If you wanted to modulate it up, you can. That's also a BPSK signal set because the two members of the signal set obey this relationship. You can see here I have a positive sine wave, and here I have a negative sine wave. So they are still BPSK. Now the important thing about signals in a signal set is that they are of finite duration. Because what's going to happen, we're going to send one bit after another, and that means each signal that represents a single bit has to only take a specific amount of time, and we call that time capital T, and it's known as the bit interval. Time taken to transmit a single bit. Well, this has an important consequence because now the data rate, the rate at which we send bits, is given by the reciprocal of that time interval. So whatever the time interval is, the data rate is the reciprocal. So if you have a 1 megabit per second transmission rate That corresponds to a time of 1 microsecond. 1 microsecond has been used for each bit. And so there's a direct relationship here. And we'll see this has important consequences in just a second. All right. Now here I'm showing an example of sending a bit sequence 0, 1, 1, 0, one after another, and you can see how we just tack on each signal from the signal set one after another to produce the transmitted waveform. You could be modulated or not, doesn't really matter, but that's why they're a finite duration. We simply go one after another until we finally represent our bit sequence with analog signals. And again, the receiver is going to be worrying about trying to figure out what the bit sequence was from this analog signal. Now, another signal set is the FSK signal set. Stands for frequency shift keying. And here we're going to use sine waves to represent the bits, but with two different frequencies. Usually these frequencies are harmonic to the bit interval. And in this example, I show a frequency of 0 that's 3 over capital T. And here I show an F1 that's 4 over capital T. And that is a typical FSK signal set. They could be different harmonics. Higher harmonics could be separated by more than one harmonic number, whatever your choice may be. The P of T in this formula has to do with the fact these are finite durations, so I'm multiplying by pulse. So these are not sine waves for all time. They again have duration T. So there's a data rate related to the reciprocal of T, just like in the BPSK case. And here is what it looks like when you have that same bit sequence. It's a bit more subtle what the difference between the 0 and 1 is, but hopefully there are receivers that can figure this out. Now, what is the transmission bandwidth? How much analog bandwidth in hertz is taken by sending a sequence of bits? Well, the one problem that comes up right away is that bandwidth depends on what the bit sequence is itself. So let me show you this by a simple example. Suppose this is time, and here are my bit intervals. And let's suppose the bit sequence I'm trying to represent is 0, 0, 0, 0. Well, the signal that represents that for our signal BPSK baseband signal set is a constant. And that constant has no bandwidth. It's a constant basically for all time. And clearly that's not going to work very well. If I have my alternate bit sequence that I showed in previous slides, now the transmitted signal looks like this, which has a bandwidth, has a wider bandwidth certainly than a constant signal. What signal set, not the signal set, what bit sequence gives you the worst case bandwidth? I've given, it's clearly not the constant bit sequence, that has no bandwidth. And the one I showed here, is there one that's worse, that has a higher frequency content than these? And the answer, of course, is the alternating bit sequence is the worst. Because now the signal goes back and forth, back and forth, back and forth. We know what the spectrum of this is. This is a square wave. So, we right away, using Fourier series, we know what the spectrum is of this worst case bit sequence represented by a baseband BPSK signal set. We know that its spectrum is given by 2 over j pi k for k odd. But one thing to note is what the period is here. One period here is twice the bit interval. So that's why it's a harmonic of 2t. rather than we use capital T to represent a period when we talked about square waves. But the period here is 2t, where t is now the bit interval. Okay, now, one consequence of this is that we know that the spectrum is basically infinitely long. So if we have something at the first harmonic, the third, the fifth, the seventh, etc., the bandwidth is basically infinite. And so we have a more practical definition of bandwidth, and that is to use what's called the 90% bandwidth. So we want to worry about something that's similar to what we talked about in terms of total harmonic distortion. I want to figure out how many Fourier series coefficients are needed so that I grab 90% of the power. And so here's the idea. We have a spectrum of the baseband signal set, for example, which is like this. Right, the first and the third harmonics. How far do I have to go out so that the total power in these harmonics is 90% of the total power? And it turns out when you do the calculations for the square wave, it turns out it's almost exactly, it is exactly the third harmonic. So the bandwidth that we care about is this bandwidth right there. And so this harmonic number corresponds to an absolute frequency of 2 over t. So the bandwidth is 3 over 2t. So it's 3/2 of the data rate. The bandwidth taken to transmit our 1 megabit per second signal is 1.5 megahertz. And this is in general true. You need a larger bandwidth in hertz than you do in data rate measured in bits per second. When you modulate the baseband signal set, as we know, the bandwidth doubles because now you have to measure things on either side of the center frequency. So now the bandwidth taken is 3R. It requires a larger bandwidth to transmit it modulated than at baseband. But as we know, we are forced to use modulation in most cases anyway, because wireless and wireline channels really work the best at higher frequencies than baseband. Now, the transmission bandwidth for FSK is a bit more complicated to derive. So I'm again going to use my worst case bit sequence here. And think about this FSK signal as a superposition. So what I have is a F0 sine wave multiplied by a square wave, and here I have an F1 frequency sine wave multiplied by a square wave, but they're out of phase with respect to each other, and all we do is add these up, and that gives us the transmitted signal. If I can figure out the bandwidth of each, then I'm in good shape. I can figure it out what the total bandwidth is by, since their spectra have to add, I think I have a way of getting at it. But it's again a square wave. Okay, so I think we can calculate that spectrum just like we did before. I'm going to assume that the carrier frequencies are harmonics of the bit interval, K0 and K1, to be completely general. Now, it turns out, here's a little detail here, in that these square waves have a non-zero value. Their average values are not zero, which means C0 is not zero in the Fourier series. So the spectrum, before you modulate it up, of that square wave has a value at the origin, a value at the first harmonic, and some smaller value given by the formula at the third harmonic. So now what's the bandwidth? Well, now, since there's a non-zero component at the origin, the bandwidth, it turns out the 90% bandwidth is now this. it turns out it occurs for, just have to go to the first harmonic. Now, when you now want to think about what the modulated spectrum looks like, we ought to draw a little picture here. So after we modulate, okay, we modulate up to F0, we have our center. We go up to the first harmonic on either side, and so this is has a bandwidth now of some amount, but we worried about the total bandwidth of the entire FSK signal set. So we draw the other signal, let's say it's F1, it too looks like that. So the bandwidth is going to go from the lowest frequency for F0 up to the highest frequency for F1. So that's what I show in these equations. We want the lowest frequency that's required for the 90% bandwidth for FSK is given by this, the highest frequency given by that. And putting it in terms of harmonic numbers, you get these relationships, subtract those upper and lower frequencies, and you get the following expression when all is said and done, relating it to data rate, which is 1 over t. So it's the difference of the harmonic numbers plus 1 times the data rate, turns out to be the bandwidth of FSK. All right? So it's interesting to compare BPSK and FSK. So since the FSK is a modulated signal set, to be fair, we need to consider a modulated version of BPSK. So we found that the bandwidth for BPSK is 3 times the data rate. Well, it turns out if you use adjacent harmonic numbers, the bandwidth for FSK is more efficient. For the same data rate, you can send a digital sequence of bits in a smaller bandwidth, and a significantly smaller bandwidth. Of course, if you don't pick adjacent numbers, harmonic numbers, this bandwidth goes up. But it's interesting that you can now directly compare and worry about the efficiency of the communication scheme, efficiency at least in terms of bandwidth required in the channel. So, in digital communication, what we do is we assign a signal set to each bit, and these signals have to be of finite duration. It's really important, so we can send one bit after another. The data rate is determined both by the source and the channel. Now, what I mean by that is we've discovered that whatever choice we make for a signal set, that demands a certain amount of bandwidth. Well, the channel has to be able to support that kind of bandwidth. In other words, it cannot narrowband filter the signal so much that it impinges upon the bandwidth that's required to send the bits. So the data rate determines what the bandwidth is in most cases. There's another issue, though, is that this source is putting out bits at a given rate. You probably want to send those bits through the channel as they emerge from the source. The transmission scheme has to keep up, if not get ahead of what the source is doing. If the transmitter works at a lower rate than the source, there's going to be a problem. There's going to be backlog of bits that have to be sent. So in most cases, you have to keep up. That's why I say the data rate is determined by the source, ultimately. How fast is this source putting out those bits? And then secondly, by the channel in the terms of its bandwidth. Does it have the bandwidth to send those bits? So the signal set choice affects the bandwidth, and we've already seen that FSK can be a bit more efficient. But the one other thing that we need to consider is reception performance. Don't forget that this channel adds noise and it attenuates the signal. This has an effect on how accurately the bits we get out are the same as the bits we sent. And so it turns out signal set choice affects that also. That's what we're going to talk about in the next video.